The Washington administration test, particularly the calculation section, has raised concerns about its fairness and necessity. Several key points highlight these concerns. Firstly, the difficulty of the test. Extensive study and external validation of calculation skills have not guaranteed success, suggesting the test may be excessively difficult. Secondly, the test's limited real-world relevance. The need for precise calculations within a short time frame may not reflect real-world scenarios, where administrators often consult with engineers or upgrade conductors for safety. Thirdly, the barriers it creates for small businesses. Requiring a highly skilled administrator with specific calculation abilities can challenge small businesses, especially those relying on part-time administrators. Fourthly, potentially unfair enforcement. Threatening to shut down a business due to technicalities regarding administrator availability, especially after prior approval, seems excessive. Considering these points, several questions arise. Is the administration test an accurate measure of an administrator's competence in the field? Does the test serve a legitimate purpose in maintaining safety and quality standards? Is the level of difficulty justified, or does it create an unnecessary barrier? Are there alternative ways to assess an administrator's knowledge and skills? Is it reasonable to expect administrators to perform precise calculations under time pressure in real-world scenarios? Are the consequences of failing the test commensurate with the potential risks posed by electrical work? Are the state's enforcement actions consistent with fairness and proportionality? To address these concerns, consider these suggestions. Firstly, re-evaluate the test's content and difficulty to align with actual needs in the field. Secondly, explore alternative assessment methods emphasizing practical skills and knowledge over precise calculations. Thirdly, provide more flexibility in administrator requirements to accommodate small businesses and unique circumstances. Fourthly, ensure enforcement actions are based on objective evidence of safety violations, not punitive measures. Fifthly, foster a collaborative relationship between the state and electrical professionals to ensure regulations are fair and effective. This is a critical evaluation to improve fairness and relevance in the electrical administration process. Understanding voltage drop is essential in electrical systems to ensure that electrical equipment receives the correct voltage to operate efficiently and safely. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. This is important because excessive voltage drop can lead to equipment malfunction, overheating, and even safety hazards. Several factors influence voltage drop, including the conductor's length, the current flowing through it, the conductor's material, and its cross-sectional area. Longer conductors have higher resistance, leading to a greater voltage drop. Similarly, higher current flowing through the conductor increases voltage drop. Different materials have different resistivity. For instance, copper has a lower resistivity than aluminum, making it a better conductor. A larger cross-sectional area reduces resistance, thereby reducing voltage drop. The formula for calculating voltage drop is as follows: volts drop equals current, measured in amps, times resistance, measured in ohms. In a direct current circuit, the voltage drop is simply the product of the current and the resistance. However, in alternating current circuits, the calculation is slightly more complex due to the presence of impedance, which includes both resistance and reactance. Reactance arises from the inductance and capacitance in the circuit. Therefore, the AC voltage drop calculation considers the impedance rather than just the resistance. To minimize voltage drop, there are several strategies that can be implemented. Firstly, using larger conductors. Increasing the cross-sectional area of the conductor reduces its resistance. Secondly, shortening the conductor length. Shorter conductors have less resistance and therefore less voltage drop. Thirdly, using conductors with lower resistivity. Copper is generally preferred over aluminum due to its lower resistivity, although aluminum is lighter and more cost-effective for some applications. Fourthly, reducing the current. Lowering the current reduces voltage drop, but might not always be practical depending on the load requirements. Fifthly, employing voltage compensation techniques. These techniques include using transformers to step up the voltage of the source to compensate for the voltage drop along the conductor. Several standards and regulations provide guidelines for acceptable voltage drop limits. The National Electrical Code, or NEC, recommends that voltage drop on branch circuits should not exceed 3% and the total voltage drop on feeders and branch circuits combined should not exceed 5%. These limits ensure that equipment operates within its designed voltage range. Exceeding these limits can cause various problems, including reduced lighting intensity, motor overheating, and inaccurate electronic device readings. In practical applications, voltage drop calculations are crucial for designing efficient and safe electrical systems. For example, when installing a long run-of cable to power a motor, it is necessary to calculate the expected voltage drop to ensure that the motor receives adequate voltage. If the voltage drop is too high, a larger conductor size must be selected. Similarly, in lighting systems, voltage drop can cause lights to dim at the end of a long circuit. This can be mitigated by using larger conductors or by splitting the load into multiple circuits. In summary, understanding and managing voltage drop is essential for maintaining the performance and safety of electrical systems. By considering the factors that influence voltage drop and implementing appropriate mitigation strategies, electrical professionals can design systems that deliver reliable power to all connected equipment. When performing voltage drop calculations, several practical considerations must be taken into account to ensure accuracy and effectiveness. These considerations range from selecting the right conductor size to accounting for temperature variations and bundling effects. Firstly, conductor size selection is paramount. The size of the conductor directly affects its resistance, which in turn impacts voltage drop. Using the appropriate conductor size involves balancing the need for minimal voltage drop with cost considerations. Larger conductors are more expensive but provide lower resistance. To select the correct size, electrical codes like the NEC provide tables that list the allowable ampacities for various conductor sizes and types. These tables help determine the minimum conductor size needed to carry the expected current without overheating. Additionally, voltage drop calculation tools and software can aid in determining the optimal conductor size for a specific application. Secondly, conductor length accuracy is essential. Accurate measurement of conductor length is critical for precise voltage drop calculations. Even small errors in length measurement can lead to significant discrepancies in the calculated voltage drop, especially in long runs. When measuring conductor length, it is important to account for all bends and turns in the wiring path. Laser distance meters and measuring wheels can provide accurate measurements, ensuring that the calculated voltage drop closely matches the actual voltage drop in the installed system. Thirdly, temperature correction is a crucial factor. The resistance of a conductor changes with temperature. As the temperature increases, the resistance also increases, leading to a higher voltage drop. Electrical codes provide temperature correction factors that adjust the conductor's ampacity based on the ambient temperature. These correction factors are applied to the conductor's base ampacity rating to determine its allowable ampacity at the operating temperature. Neglecting temperature correction can result in undersizing the conductor, leading to excessive voltage drop and potential overheating. Fourthly, bundling and proximity effects need consideration. When multiple conductors are bundled together or run in close proximity, the heat dissipation capability is reduced. This can lead to higher operating temperatures and increased resistance. Electrical codes provide adjustment factors for bundled conductors to account for this effect. These adjustment factors reduce the allowable ampacity of each conductor in the bundle. Ignoring bundling effects can result in conductors operating at higher temperatures than intended, leading to increased voltage drop and potentially reducing the lifespan of the insulation. Fifthly, load characteristics play a significant role. The type of load connected to the circuits also affects voltage drop. Resistive loads, such as heaters and incandescent lights, draw a constant current. Inductive loads, such as motors and transformers, draw a varying current, especially during startup. The inrush current of inductive loads can cause a significant temporary voltage drop. Voltage drop calculations should consider the load's maximum expected current, including any inrush currents. For inductive loads, it may be necessary to use larger conductors or voltage compensation techniques to mitigate the effects of inrush current. Sixthly, voltage source stability is important. The stability of the voltage source affects the accuracy of voltage drop calculations. If the voltage source fluctuates, the actual voltage drop may vary from the calculated value. It is important to ensure that the voltage source is stable and within the specified voltage range. Voltage regulators can be used to stabilize the voltage source, ensuring that the voltage drop remains within acceptable limits. Seventhly, using appropriate calculation methods is necessary. Different calculation methods are used for direct current DC and alternating current AC circuits. In DC circuits, the voltage drop calculation is straightforward. Volts drop equals current times resistance. In AC circuits, the calculation is more complex due to the presence of reactance. The AC voltage drop calculation considers the impedance of the circuit, which includes both resistance and reactance. Using the correct calculation method is essential for accurate results. Voltage drop calculators and software tools can simplify these calculations, but it is important to understand the underlying principles to ensure that the results are valid. Eighthly, grounding and bonding considerations are relevant. Proper grounding and bonding are essential for safety and also affect voltage drop. Grounding provides a low impedance path for fault currents, helping to protect against electrical shock. Bonding ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electrical shock and minimizing voltage drop. Grounding and bonding conductors must be sized according to electrical codes to ensure their effectiveness. In summary, accurate voltage drop calculations require careful consideration of several factors, including conductor size, conductor length, temperature correction, bundling effects, load characteristics, voltage source stability, calculation methods, and grounding and bonding. By addressing these practical considerations, electrical professionals can design and install electrical systems that provide reliable power and operate safely. Understanding conductor properties and their impact on electrical systems is crucial for designing safe and efficient installations. Several key properties determine how a conductor behaves, including conductivity, ampacity, resistance, and insulation. Firstly, conductivity refers to a material's ability to conduct electric current. Materials with high conductivity allow current to flow easily with minimal resistance, while materials with low conductivity impede current flow. Copper and aluminum are the most commonly used conductors in electrical systems due to their high conductivity. Copper has a slightly higher conductivity than aluminum, but aluminum is lighter and more cost-effective for certain applications. The conductivity of a material is typically measured in Siemens per meter S/m. Secondly, ampacity, or current carrying capacity, is the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. Ampacity is determined by several factors, including the conductor's size, material, insulation type, and the ambient temperature. Electrical codes, such as the NEC, provide tables that list the allowable ampacities for various conductor types and sizes. These tables help ensure that conductors are not overloaded, which can lead to overheating, insulation damage, and even fire hazards. Ampacity is measured in amps. Thirdly, resistance is the opposition to the flow of electric current in a conductor. Resistance is affected by the conductor's material, length, and cross-sectional area. Longer conductors have higher resistance, and conductors with smaller cross-sectional areas also have higher resistance. Resistance is measured in ohms. The relationship between resistance, voltage, and current is described by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. Understanding resistance is essential for calculating voltage drop and ensuring that electrical equipment receives the correct voltage. Fourthly, insulation is the non-conductive material that surrounds a conductor to prevent electrical current from flowing where it is not intended. Insulation protects against electrical shock and prevents short circuits. Various types of insulation are used in electrical systems, each with different temperature ratings and properties. Common insulation materials include polyvinyl chloride, PVC, cross-linked polyethylene, XLPE, and rubber. The insulation's temperature rating indicates the maximum temperature at which the conductor can operate without degrading the insulation. Electrical codes specify the appropriate insulation type for different applications based on factors such as voltage, temperature, and environmental conditions. The selection of conductors in electrical systems depends on several factors, including the application's requirements, cost considerations, and environmental conditions. Copper conductors are often preferred for their high conductivity and corrosion resistance, making them suitable for a wide range of applications. However, aluminum conductors are lighter and more cost-effective for large installations, such as overhead power lines. When selecting a conductor, it is important to consider its ampacity, voltage rating, and insulation type to ensure that it meets the requirements of the application. The NEC provides guidelines for conductor selection based on these factors. Furthermore, environmental conditions such as temperature, moisture, and exposure to chemicals can affect the performance and lifespan of conductors. Conductors used in harsh environments may require special insulation or protective coatings to prevent corrosion and degradation. Regular inspection and maintenance of conductors are essential for ensuring their continued safe and reliable operation. This includes checking for signs of damage, such as cracks, corrosion, and overheating, and replacing conductors as needed. Proper installation practices, such as using the correct connectors and avoiding sharp bends, can also help extend the lifespan of conductors. In summary, understanding conductor properties is crucial for designing safe and efficient electrical systems. By considering factors such as conductivity, ampacity, resistance, and insulation, electrical professionals can select the appropriate conductors for each application and ensure their reliable operation. The proper installation and maintenance practices also play a vital role in maximizing the performance and lifespan of conductors. In electrical systems, circuit breakers and fuses are crucial overcurrent protection devices that safeguard equipment and prevent hazards. While both serve the same basic function, they operate differently and have distinct characteristics. Understanding these differences is essential for selecting the appropriate overcurrent protection for a given application. Firstly, circuit breakers are electromechanical devices that automatically interrupt the flow of current in a circuit when an overcurrent condition is detected. They consist of a bimetallic strip or a magnetic coil that responds to excessive current. When an overcurrent occurs, the bimetallic strip heats up and bends, or the magnetic coil becomes energized, causing the breaker to trip and open the circuit. Circuit breakers can be reset manually or automatically after the fault is cleared, making them reusable. Secondly, fuses are one-time use devices that protect circuits by melting a fusible link when an overcurrent occurs. The fusible link is a metal wire or strip designed to melt at a specific current level. When the current exceeds this level, the link melts, opening the circuit and stopping the flow of current. Once a fuse has blown, it must be replaced with a new one of the same type and rating. Several types of circuit breakers and fuses are available, each designed for specific applications and current levels. Common types of circuit breakers include standard thermal magnetic breakers, ground fault circuit interrupters, GFCIs, and arc fault circuit interrupters, SIs. Standard thermal magnetic breakers are the most common type and are used for general-purpose circuit protection. GFCIs protect against ground faults, which can cause electrical shock. SIs protect against arc faults, which can cause fires. Common types of fuses include cartridge fuses, plug fuses, and blade fuses. Cartridge fuses are used in a wide range of applications, from residential to industrial. Plug fuses are typically used in older residential panels. Blade fuses are commonly used in automotive applications. The selection of circuit breakers and fuses depends on several factors, including the circuit's voltage, current rating, and the type of load being protected. It is important to select an overcurrent protection device with a current rating that is appropriate for the circuit. The current rating should be high enough to allow normal current flow, but low enough to trip or blow when an overcurrent occurs. Electrical codes, such as the NEC, provide guidelines for selecting the appropriate overcurrent protection for different types of circuits and loads. Proper installation and maintenance of circuit breakers and fuses are essential for ensuring their continued safe and reliable operation. This includes ensuring that they are properly sized, installed, and maintained according to the manufacturer's instructions and electrical codes. Regular inspection and testing of circuit breakers and fuses can help identify potential problems before they lead to failures. It is important to replace any circuit breakers or fuses that show signs of damage, such as cracks, corrosion, or overheating. In summary, circuit breakers and fuses are essential overcurrent protection devices that safeguard electrical systems and prevent hazards. Understanding their differences and selecting the appropriate type and rating are crucial for ensuring safe and reliable operation. Proper installation and maintenance practices also play a vital role in maximizing their effectiveness and lifespan. Electrical grounding and bonding are essential safety measures that protect people and equipment from electrical shock and damage. Grounding provides a low impedance path for fault currents, allowing overcurrent protection devices to quickly trip and energize the circuit. Bonding ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electrical shock. Firstly, grounding refers to connecting the electrical system to the earth, typically through a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode provides a low resistance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and energize the circuit. Grounding helps prevent voltage buildup on metallic parts of the electrical system, reducing the risk of electrical shock. Secondly, bonding refers to connecting all metallic parts of the electrical system together to create a low impedance path for fault currents. This includes metal conduits, equipment enclosures, and metallic water pipes. Bonding ensures that all metallic parts are at the same potential, reducing the risk of electrical shock if someone comes into contact with two different metallic parts at different voltages. The NEC requires that all metallic parts of the electrical system be bonded together to create an effective ground fault current path. Several types of grounding and bonding methods are used in electrical systems, depending on the application and the type of electrical system. Common grounding methods include system grounding, equipment grounding, and separately derived system grounding. System grounding refers to grounding the neutral conductor of the electrical system. Equipment grounding refers to grounding the non-current carrying metallic parts of equipment. Separately derived system grounding refers to grounding systems that are not directly connected to the main electrical system, such as generators and transformers. Common bonding methods include using bonding jumpers to connect metallic parts together and using metal conduits as a bonding means. The selection of grounding and bonding methods depends on several factors, including the type of electrical system, the voltage level, and the environmental conditions. Electrical codes, such as the NEC, provide detailed requirements for grounding and bonding electrical systems. Proper installation and maintenance of grounding and bonding systems are essential for ensuring their continued safe and reliable operation. This includes ensuring that grounding electrodes are properly installed and that all metallic parts are properly bonded together. Regular inspection and testing of grounding and bonding systems can help identify potential problems before they lead to failures. It is important to repair any damaged or corroded grounding and bonding connections. In summary, electrical grounding and bonding are essential safety measures that protect people and equipment from electrical shock and damage. Understanding the principles of grounding and bonding and following electrical code requirements are crucial for ensuring safe and reliable electrical systems. Proper installation and maintenance practices also play a vital role in maximizing the effectiveness of grounding and bonding systems. Electrical transformers are essential components in electrical power distribution systems, used to step up or step down voltage levels to match the requirements of different equipment and applications. They operate on the principle of electromagnetic induction, transferring electrical energy from one circuit to another without direct electrical connection. Understanding transformer types, operation, and maintenance is crucial for electrical professionals. Firstly, transformer types vary based on their application, construction, and installation methods. Step-up transformers increase voltage, while step-down transformers decrease voltage. Isolation transformers provide electrical isolation between circuits. Autotransformers use a single winding for both primary and secondary circuits. Tri-type transformers use air as the cooling medium, while liquid-filled transformers use oil or other insulating liquids for cooling and insulation. Secondly, transformer operation is based on Faraday's law of electromagnetic induction. A transformer consists of two or more coils of wire, called windings, wound around a common iron core. The primary winding is connected to the source voltage, and the secondary winding is connected to the load. When alternating current flows through the primary winding, it creates a magnetic field in the core. This magnetic field induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. Thirdly, transformer maintenance is essential for ensuring their reliable operation and prolonging their lifespan. Regular inspection should include checking for oil leaks, corrosion, and damage to the windings and insulation. The oil level in liquid-filled transformers should be checked and maintained. Bushings and connections should be inspected for tightness and cleanliness. Insulation resistance tests can help detect insulation degradation. Thermographic surveys can identify hotspots caused by loose connections or overloaded windings. Fourthly, transformer installation requires careful consideration of several factors, including location, ventilation, and protection. Transformers should be installed in a well-ventilated area to prevent overheating. They should be protected from physical damage and environmental hazards. Overcurrent protection devices, such as circuit breakers and fuses, should be installed to protect the transformer from overload and short circuits. Grounding is essential for safety and should be done according to electrical code requirements. Fifthly, transformer selection depends on the application's voltage and power requirements. The transformer's voltage rating should match the source and load voltages. The transformer's kilovolt ampere, or kV, rating should be sufficient to handle the load's power requirements. It is important to consider factors such as efficiency, impedance, and harmonic distortion when selecting a transformer. Sixthly, transformer efficiency is the ratio of output power to input power. High-efficiency transformers can save energy and reduce operating costs. Transformer impedance affects the voltage regulation and short-circuit current. Harmonic distortion can cause overheating and damage to the transformer. In summary, electrical transformers are essential components in electrical power distribution systems. Understanding transformer types, operation, installation, maintenance, and selection is crucial for electrical professionals to ensure safe, reliable, and efficient operation. Regular inspections, proper maintenance, and adherence to electrical codes are essential for prolonging the lifespan of transformers and preventing failures. Electrical motors are essential devices that convert electrical energy into mechanical energy, powering a wide range of applications from household appliances to industrial machinery. Understanding motor types, operation, and control is crucial for electrical professionals. Firstly, motor types vary based on their construction, operating principles, and application requirements. Alternating current (AC) motors include induction motors, synchronous motors, and wound rotor motors. Direct current (DC) motors include series motors, shunt motors, and compound motors. Induction motors are the most common type, used in a wide range of applications due to their simplicity, reliability, and low cost. Secondly, motor operation is based on the principle of electromagnetic induction. An electric current flowing through a coil of wire in a magnetic field experiences a force that causes the motor to rotate. AC motors use alternating current to create a rotating magnetic field, which interacts with the rotor to produce torque. DC motors use direct current to create a static magnetic field, which interacts with the armature to produce torque. Thirdly, motor control is essential for starting, stopping, and regulating the speed and torque of electric motors. Motor starters are used to limit the inrush current during startup. Variable frequency drives, VFDs, are used to control the speed and torque of AC motors. Programmable logic controllers, PLCs, are used to automate motor control processes. Fourthly, motor maintenance is crucial for ensuring their reliable operation and prolonging their lifespan. Regular inspections should include checking for overheating, vibration, and unusual noise. Bearings should be lubricated regularly. Windings should be tested for insulation resistance. Cooling fans should be cleaned to prevent overheating. Fifthly, motor installation requires careful consideration of several factors, including location, ventilation, and protection. Motors should be installed in a well-ventilated area to prevent overheating. They should be protected from physical damage and environmental hazards. Overload protection devices, such as thermal overload relays, should be installed to protect the motor from overload conditions. Grounding is essential for safety and should be done according to electrical code requirements. Sixthly, motor selection depends on the application's power and speed requirements. The motor's horsepower rating should be sufficient to handle the load's power requirements. The motor's speed rating should match the application's speed requirements. It is important to consider factors such as efficiency, torque, and duty cycle when selecting a motor. Seventhly, motor efficiency is the ratio of output power to input power. High-efficiency motors can save energy and reduce operating costs. Motor torque is the rotational force that the motor can produce. Motor duty cycle is the percentage of time that the motor is operating under load. In summary, electrical motors are essential devices that convert electrical energy into mechanical energy. Understanding motor types, operation, control, installation, maintenance, and selection is crucial for electrical professionals to ensure safe, reliable, and efficient operation. Regular inspections, proper maintenance, and adherence to electrical codes are essential for prolonging the lifespan of motors and preventing failures. The selection and sizing of electrical wiring and conduit are critical aspects of electrical system design, ensuring safety, efficiency, and compliance with electrical codes. Proper selection and sizing prevent overheating, voltage drop, and potential hazards. Firstly, wiring selection involves choosing the appropriate type and size of conductor for a given application. Factors to consider include the ampacity, voltage rating, insulation type, and environmental conditions. The ampacity of a conductor is its current carrying capacity, which must be sufficient to handle the load's maximum current demand. The voltage rating must be equal to or greater than the circuit voltage. The insulation type must be appropriate for the operating temperature and environmental conditions. Secondly, conduit selection involves choosing the appropriate type and size of conduit for protecting electrical wiring. Conduit provides mechanical protection for wiring, protects against environmental factors, and helps prevent electrical shock and fire hazards. Common types of conduit include rigid metal conduit (RMC), intermediate metal conduit (IMC), electrical metallic tubing (EMT), and flexible metal conduit. Thirdly, wiring sizing is determined by the load's current demand, the conductor's ampacity, and the allowable voltage drop. Electrical codes, such as the NEC, provide tables that list the allowable ampacities for various conductor types and sizes. Voltage drop calculations are used to determine the minimum conductor size needed to ensure that the voltage at the load is within acceptable limits. Fourthly, conduit sizing is determined by the number and size of conductors to be installed in the conduit. The electrical codes provide tables that list the maximum number of conductors allowed in various conduit sizes. It is important to ensure that the conduit is not overcrowded, which can make it difficult to pull the wiring and can cause overheating. Fifthly, deterring factors are applied to conductor ampacities when multiple conductors are installed in the same conduit or cable. Deterring factors account for the increased heat generated by multiple conductors and reduce their allowable ampacities. Electrical codes provide deterring factors for various numbers of conductors and ambient temperatures. Sixthly, voltage drop calculations are used to determine the minimum conductor size needed to ensure that the voltage at the load is within acceptable limit. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends that voltage drop on branch circuits should not exceed 3% and the total voltage drop on feeders and branch circuits combined should not exceed 5%. Seventhly, grounding conductors must be properly sized and installed to provide a low impedance path for fault currents. Grounding conductors connect the non-current carrying metallic parts of equipment to the grounding electrode system. Electrical codes provide requirements for the size and installation of grounding conductors. In summary, the selection and sizing of electrical wiring and conduit are critical aspects of electrical system design. Proper selection and sizing ensure safety, efficiency, and compliance with electrical codes. Factors to consider include ampacity, voltage rating, insulation type, environmental conditions, conduit type, wiring size, conduit size, dirting factors, voltage drop calculations, and grounding conductors. Adherence to electrical codes and best practices is essential for designing safe and reliable electrical systems. Understanding electrical plans and blueprints is an essential skill for electrical professionals, enabling them to interpret design intent, identify system components, and ensure accurate installation. Electrical plans and blueprints provide a visual representation of the electrical system, including wiring diagrams, equipment layouts, and control schematics. Firstly, electrical plans typically include floor plans that show the layout of the building, including walls, doors, windows, and other architectural features. Electrical symbols are used to represent various electrical components such as lighting fixtures, receptacles, switches, and panel boards. Wiring diagrams show the connections between electrical components, including the size and type of conductors. Secondly, blueprints are technical drawings that provide detailed information about the electrical system. Blueprints typically include elevations, sections, and details that show the physical dimensions and construction of electrical equipment and systems. Blueprints also include schedules that list the specifications for electrical equipment, such as voltage, current, and power ratings. Thirdly, electrical symbols are standardized representations of electrical components used on electrical plans and blueprints. Understanding electrical symbols is essential for interpreting electrical plans and blueprints. Common electrical symbols include those for lighting fixtures, receptacles, switches, panel boards, motors, transformers, and control devices. Fourthly, wiring diagrams show the connections between electrical components, including the size and type of conductors. Wiring diagrams may be shown as single-line diagrams or multi-line diagrams. Single-line diagrams show the electrical system in a simplified form, with each circuit represented by a single line. Multi-line diagrams show each conductor in the circuit individually. Fifthly, equipment layouts show the physical location of electrical equipment, such as panel boards, transformers, and motors. Equipment layouts typically include dimensions and clearances to ensure that the equipment can be properly installed and maintained. Sixthly, control schematics show the operation of control systems, such as motor control circuits and lighting control systems. Control schematics use symbols to represent control devices, such as relays, timers, and switches. Seventhly, specifications provide detailed information about the electrical equipment and materials to be used in the project. Specifications typically include the manufacturer's name, model number, voltage rating, current rating, and other relevant information. In summary, understanding electrical plans and blueprints is an essential skill for electrical professionals. Electrical plans and blueprints provide a visual representation of the electrical system, including wiring diagrams, equipment layouts, and control schematics. Understanding electrical symbols, wiring diagrams, equipment layouts, control schematics, and specifications is crucial for interpreting electrical plans and blueprints accurately. The information presented in electrical plans and blueprints is used to install, maintain, and troubleshoot electrical systems.